neutrality, it is essential to produce hydrogen by harnessing renewable energy such as solar and wind energy without emitting carbon dioxide and use it as an energy source. Photoelectrochemical water electrolysis is a case in point. This technology produces hydrogen by splitting water using electric energy that is obtained by absorbing solar energy. Considering that only solar energy is necessary to obtain hydrogen, this technology is highly essential for achieving a carbon-neutral society. Developing photoelectrochemical catalysts with high catalytic activity is crucial to produce large amounts of hydrogen by improving the efficiency of photoelectrochemical water electrolysis. In the case of precious metal catalysts such as iridium and platinum, they have high catalytic activity but are expensive. That makes them unsuitable for large-scale synthesis. For this reason, there has been much research on nanostructured transition metal-based oxides, sulfides, phosphides, and etc. to replace precious metal catalysts. Recently, a research team has developed a method to obtain inexpensive catalysts while maximizing the catalytic activity of these transition metal-based catalysts. Professor Chang Oh-won's research team at Seoul National University successfully utilized atomic layer deposition to deposit iridium in the form of a single atom on transition metal-based catalysts. They have also discovered that even a small amount of iridium improves the performance of photoelectrochemical oxygen evolution reaction of photoelectrides.
As nanoparticles and nanostructures has a very large specific surface area, there has been much research on catalytic reactions in the field of energy. However, the percentage of atoms making up nanomaterials which are exposed to the surface is still less than 10%. To fully utilize all these atoms, they must be isolated instead of being attached to each other. Based on this principle, our core technology focuses on maximizing the photoelectrochemical catalytic properties and photoelectrode performance by utilizing highly active but expensive precious metals in the form of single atoms. In the photoelectrode developed by our team, the photo-absorbing layer is an N-type silicon semiconductor. Sub-nanometer thin nickel and nickel oxide catalysts are deposited on its surface as a supporting layer. In particular, nickel oxide is essentially a P-type semiconductor which has a large number of nickel vacancies on its surface. Since these nickel vacancies are energetically unstable sites, iridium atoms preferentially occupy these locations upon deposition. Based on this principle, we can produce iridium single atom catalysts that are completely isolated each other.
The team's development is detailed as follows. We deposit a zirconium oxide thin film which acts as a passivation layer and a nickel thin film which acts as a catalyst on an N-type silicon photoelectrode through electron beam evaporation. Then we apply atomic layer evaporation using an iridium precursor and oxygen gas to deposit iridium in the form of a single atom. In this process, the nickel thin film reacts with oxygen to form nickel oxide on the surface, and iridium is located in the nickel vacancies of the nickel oxide in the form of a single atom. The iridium single atom obtained in this way has a unique oxidation number of +3 to +4 due to its interaction with the oxygen atoms present in the nickel oxide. Professor Chang Oh-won's research team has demonstrated that when they compared a photoelectrode with iridium single atom catalysts with a photoelectrode with thin film iridium, the mass activity of iridium is 679 times higher. This is a result of the independent existence of all the iridium atoms, maximizing utilization efficiency. These single atoms have an enormous potential in the field of catalysts for green hydrogen production. For metal single atoms, the electrons present in the d orbital can play a key role in enhancing the catalytic activity by participating in electron transfer and interaction with the reactant. Furthermore, the strong metal support interaction with support materials plays a vital role in modifying the electronic and chemical properties of the metal atoms, enhancing the activity and selectivity of the catalyst.
Single atom catalysts exhibit unique electronic and chemical properties that cannot be obtained from existing nanostructured catalysts. Therefore, we believe that if we utilize them effectively, we can obtain practical catalysts with significantly higher water electrolysis efficiency. In particular, multi-component single-atom catalysts, which use more than 2 metal elements, have various types of electronic properties and orbital filling. This will optimize the binding energy and reaction pathway with reaction intermediates. Moreover, using cost-effective and abundantly available non-precious metal single-atom catalyst could further reduce the cost of hydrogen production.
Thanks to these excellent catalytic properties and cost-effectiveness of single-atom catalysts, there has been active research on diverse catalytic reactions related to energy conversion. More specifically, single-atom catalysts are being applied to hydrogen evolution reactions and oxygen evolution reactions in water electrolysis, oxygen reduction reactions in fuel cells, carbon dioxide reduction reactions, nitrogen reduction reactions, and organic synthesis reactions.
Our team is the first in the world to develop a method for depositing single-atom catalyst on silicon-based photoelectrode. We have uncovered the unique electronic states and excellent photoelectrochemical properties of the single atoms. We expect that this revolutionary research result will play a key role in hydrogen production technology harnessing solar energy. We also expect that our research will set new standards for the technology of synthesizing precious metal catalysts with high utilization efficiency in various energy conversion fields utilizing solar energy.
The research on the photoelectrochemical catalytic properties of iridium single-atom catalysts has been published in the renowned journal Nature Communications. The research team was recognized for maximizing photoelectrochemical utilization efficiency of atoms which exist independently. The team's passion for breaking the economic threshold of green hydrogen production is noticeable. Hopefully, their research will accelerate the practical application of green hydrogen and contribute to the realization of a carbon-neutral society in the near future.